The boosting algorithm presented so far can be applied to any learning procedure, allowing to train the individual predictors composing the final model. Version of boosting, called gradient boosting decision trees, specifically designed to take into account decision trees as individual predictors, exist. One such boosting algorithm, called multiple additive regression trees and based on shallow decision trees, was created by Friedman and Mullman in 2003. The most notable difference in this algorithm comes from equation 9. Just before this step, as with generic boosting, a tree is trained on the residuals. However, instead of storing the entire decision tree in memory, i.e. both the partition associated with this tree, but also the optimal value computed in each cell, only the partition, i.e. the set of terminal cells of the tree, is stored. Let us note R1 through Rj, the leaves of the tree Ht, learned in this step. In the next step, instead of optimizing the parameter alpha in an approximate way via backtracking line search, we will optimize each of the values associated with the leaves of the tree Ht. In each leaf of the tree, we look for the optimal value of the prediction, allowing to minimize the corresponding term in equation 9. Indeed, the term on the right-hand side of equation 9 can be decomposed into a sum of terms, each of which relates to only one of the leaves of the tree, indexed from 1 to j. We thus replace the approximate optimization via backtracking line search by an exact optimization of a more general problem. Previously, we were looking for an optimal value of alpha. We now look for j optimal values, alpha 1 until alpha j, where j is the number of leaves in the tree. This procedure is therefore exact and much faster than the previous procedure because the optimization can be performed exactly, without any iteration. Tree boosting algorithms are directly accessible in scikit-learn via the functions gradient boosting classifier for classification and gradient boosting regressor for regression. Several parameters are very important in the boosting procedure. First, the number of elementary predictors, i.e. the number T of trees, or equivalently the number of iterations. This parameter controls the statistical complexity of the final predictor. The larger the number of trees composing the final predictor, the more complex this predictor is. Therefore, when T is large, the boosting predictor can approach complex functions with large variations. The parameter T also controls the number of iterations of the optimization procedure. In order to decouple the statistical complexity and the number of iterations of the algorithm, the regularization parameter nu is introduced. This parameter avoids overfitting in the first iterations of the algorithm by preventing the addition of a perfect predictor. If a perfect predictor is chosen, the new parameter weights its influence on the aggregated predictor. We can also see boosting as a gradient descent method. At each iteration, we take a step in the opposite direction of the loss gradient by adding the predictor ht with a weight alpha t. The parameter nu can thus be seen as the learning rate of the gradient descent. The smaller this parameter nu is, the more iterations are needed to converge. By choosing a high value of t and a low value for the parameter nu, we can thus obtain a correctly optimized complex predictor. A classical practice is to set nu to a low value, typically 0.1. The number of trees t may be fixed to 100, for example, or optimized by early stopping, i.e. by splitting the dataset into a training set and a validation set, and by stopping the iterations when the performance of the aggregated predictor on the validation set starts to decrease. The tree construction procedure is the same as the one described in the decision tree session, which is also the procedure used in random forest. However, no split randomization is applied in boosting. The max features parameter is set to d. Another difference compared to the trees used in random forest is their depth. The maximum depth of a tree in the boosting procedure is typically set to 3, but is plus infinity in random forest. There is no restriction on the depth. By default, quadratic loss is used in regression and log loss is used in classification. The boosting algorithm is a state-of-the-art algorithm for supervised learning with tabular data. Boosting can therefore be used in classification and regression for a variety of loss functions. Indeed, we presented the AdaBoost algorithm for binary classification with exponential loss, but also the generic boosting algorithm that can be used for any loss and any individual learning procedure. Boosting can take into account inputs that are both continuous and discrete. It is a deterministic strategy, unlike random forest. 2 runs of the boosting algorithm lead to the same predictor. Unfortunately, this method can be computationally expensive. A large number of trees may be required to obtain good statistical performance. However, a large number of trees can lead to overfitting, which requires the use of the regularization parameter and the early stopping procedure. Moreover, this method can be sensitive to outliers or noise in the data depending on the loss used. Remember that one of the drawbacks of XGBoost is its high sensitivity to noise. Using exponential loss therefore leads to an algorithm that is not very robust to noise. The choice of other loss functions within the generic boosting algorithm allows us to reduce this sensitivity. A widely used version of tree boosting algorithm is XGBoost, Extreme Gradient Boosting, invented in 2016. This algorithm is currently one of the most powerful versions of boosting, both in terms of computational speed and predictive performance. It is a state-of-the-art algorithm on tabular data, often with better predictive performances than random forests. A first difference with the classical gradient boosting lies in the choice of the optimal tree. This choice is guided, as we have seen, by a first-order approximation in the classical algorithm, whereas a second-order approximation is used in XGBoost. In addition to the optimization objective, which is different, several procedures make XGBoost more efficient. First, discretization of the input variables according to the order statistics is used, thus limiting the search for the number of cuts to build each tree. Parallelization techniques within the construction of each tree, as well as the ability to efficiently handle sparse data, leads to a significant reduction in the computation time of the procedure. In conclusion, XGBoost is very efficient from a computational point of view and can therefore be applied to very large-scale datasets. Finally, it has in practice very good predictive performances on tabular datasets. As for random forest, it is possible to calculate variable importances based on the boosting algorithm. The two variable importances used in random forest are computable here: the MDI, because tree boosting is based on trees, and the MDA, which can be applied to any supervised algorithm. More precisely, the MDI is computed for each tree of the final boosting predictor. These MDIs are then averaged without weights to form the final MDI of the boosting predictor. The MDA is calculated in the same way as for random forest or any other algorithm, by permuting a variable in the test set and comparing the performance of the boosted predictor on the original set and the permuted set. You can see here the variable importances computing on the real estate dataset presented at the beginning of the session on decision trees. Note that, as with random forest, the order of the variables changes according to the importance measure. We must therefore be extremely careful about the conclusion we draw from such measures. The discussion of the different aspects of the variable importances for random forest also applies to those calculated with boosting. This concludes this session on random forest and tree boosting. I hope it has inspired you, and I now encourage you to look at the additional contents if you want to learn more on these methods.